In this lecture, we're going to look at compilers and interpreters. So going back a bit, back to zeros and ones, the CPU processes instructions in machine code, and the transistors, the key components that make up the CPU, only really understand on and off. So all of the instructions that the CPU processes are basically patterns of ones and zeros. These are obviously not going to be easy for humans to read or write. And so the earliest programming languages that were developed were assembly languages. These use simple mnemonic names for each machine code instruction. So for example, if pattern 0000101 represented the machine code instruction decrement B, so an instruction to decrease the number stored in a particular register by 1. So if that's the pattern 0000101, then instead we can use the mnemonic dec, DEC for decrement, dec B as the instruction instead of using the pattern of zeros and ones. And then the assembler can go through and take this slightly more readable version of the program code and turn it into zeros and ones when it's time for the computer to operate on it. And a little bit more on assembly programming language in some of the other lectures. But people can basically write using these mnemonics, which are easier to read and understand, and then translate the program into the patterns of zeros and ones for when it's time to actually run the program on the computer. Programming in assembly is possible, and indeed once upon a time that's what all computer programmers did. They had to use assembly to do programming. But it's very difficult, and any assembly language program that's developed is tied to a particular CPU design. And it's also very slow. A very simple operation, such as doing a loop to add numbers together, might require many dozens of lines of assembly code for what might be done using far fewer lines of instruction, using another a more modern programming language. So even very simple operations can require lots and lots of code. Now, handcrafted assembly can be very efficient when prepared by an expert who really understands and knows what they're doing, but it's generally not worth the time and effort required for the gain that you get from doing this manually. So Doom, and also I think a little bit in Quake, which followed it, were amongst the last major games that used significant amounts of handcrafted assembly programming. From that point on, really required just too much work to use assembly to program games, or anything else pretty much, with a few exceptions. Instead, high-level programming languages are what are used to generate the vast majority of code that is out there. Now, these are abstracted away from the low-level hardware to make the code more readable and more portable. So if you use a programming language like C or C++, you could write the program once, and in principle you should be able to compile that to run the same program on different computers that have different types of CPU in them. And they're also more powerful in that a single instruction in a high-level programming language may equate to many lines of assembly or machine code. So a routine that's got maybe half a dozen lines of code in C++ might equate to something like 60 or more lines of assembly or machine code instructions. And there is a huge range of high-level programming languages that exist. I did a survey in the class on what programming languages students have used, and I got quite a wide range of replies. The most common languages tended to be things like BASIC, C, Java, C#. In many cases it's because of the particular languages that we teach here at the university. In some cases a few other languages did pop up as examples of programming languages that different people had used. But they are really amongst the most common ones. There is also this distinction between sort of high-level and low-level programming languages. So machine code and assembly, because they're very close to the processor and each instruction only does a very small amount of work, are generally considered as low-level instructions. Programming languages like C, C++, BASIC, Java, C#, and even on to 4GL or database languages, fourth generation languages, are considered as high-level languages. Some writers and some people differentiate between higher and lower level of programming languages. C is a programming language that allows you quite a lot of direct access to the underlying hardware. At times makes it easy to deal with underlying hardware and has some low-level language features. So it's often considered as being a lower level language than the likes of Java or Visual Basic. But all of these languages up here are high-level programming languages. When we're writing in a high-level programming language, we require to use some kind of language translator. That's a piece of software, it's a program itself, and what it does, it converts some input program from one form to another. So for example, taking a high-level programming language program that has been written by a person into some low-level machine code that's ready for the computer to use. So the high-level language code usually exists in text files known as the source code. So the translator converts source code into machine code ready to run on the computer. There's a number of different execution models that programs can use as well. Interpreted languages include BASIC and a wide range of scripting languages. There are compiled languages such as C and C++. We'll come to both of those in a little while. There's also something called translated languages. So sometimes you might write code in one programming language, run it through a translator that outputs code in a different high-level programming language. So for example, you might have a translator that takes your source code in a particular, perhaps an unusual or a rare programming language, might convert that into C, which can then be compiled and optimized using a C compiler. So translated languages convert code from the form they're written in into another programming language ready for interpretation or compilation. So what are interpretation and compilation? Come to that in a second. Some more detail on this. Some of the languages usually interpreted include most versions of BASIC, JavaScript, Lua, PHP, Python, Perl, GameMaker, Ruby. So a lot of web programming languages and web scripting languages. Languages that are usually compiled include a huge range. C++ and C# are in this list, as well as a wide range of others. So what does an interpreter do? Here's a simple basic program. The first line is a comment, so it doesn't actually do anything, it's just a comment for the human reader. Second line prints a message, and the third line says go back to line 10, so it jumps back to the beginning of the program. So that program will keep running. When this basic program is run, the interpreter converts each line in turn into machine code as it is running. So the conversion to machine code occurs while the program is running. What this means is that each line is converted from source code to machine code every time that program line is encountered as the program runs. So it'll convert line 10, actually it'll skip line 10 because it's a comment, it's a remark. It will then convert line 20 into machine code, and it will do that operation, it will print out hello world. It will then convert this statement to machine code to work out what's required. Come back to here, skip this line, it's a remark, and although we're back at a line we've already run and we've already converted this to machine code before, we're actually going to convert it to machine code again before we actually operate on this and print out hello world. And that program will continue to do that. So the conversion to machine code occurs while the program is running with an interpreter. There are some advantages in that the code is often much more flexible in that you can change the source code at any time, and the translation of instructions, unfortunately, while the program is running, slows down the operation of the program, because it's not just got to carry out the instructions, it's got to convert the instructions into machine code as it goes, and that incurs a time penalty. So the lines inside the loop might be translated many times, and the availability of the source code makes it easy for others to reverse engineer the program to discover how it works and make their own versions or copies. So it's flexible. Sometimes they're easier to develop and test, but there are some downsides. In contrast, compilers convert the whole program into machine code before it can be run at all. So here we have an example of a C program, and the entire program will be converted to machine code to create an executable file that's already in machine code, and then you can run the executable file. So all the conversion is done ahead of time before you run it. The compilation for C or C++ takes place in a number of stages. First of all, source code files are pre-processed, And there's a wide range of preprocessor instructions. These are directives that allow the source code to modify itself before it's compiled. There's one example if we go back to this statement here. This hash include statement is a statement that's operated on by the preprocessor. And it tells it that it needs to take the contents of the file standardio.h and add that to this source code file before it's compiled. It needs to do that because this printf, this print function, actually exists inside the standard IO library, and so to have access to that when the program compiles, we need to include the standard IO header into this source code. So it copies this piece of some source code stored in a file called standardio.h into this file before compiling. So after the preprocessor has done its job, and there can also be commands inside the preprocessor to switch different bits of source code on and off, for example. Once that's done, the source code files are compiled. And a single project may have dozens or hundreds of different source code files that all make up one project. Each source code file that's compiled creates an object file. So this is essentially, it's a compiled output for each file in machine code, but they're kind of standalone files that need to be combined to make the final executable project. This is where a separate program called the linker comes into play. We'll see the linker in a second. So the compilation is done in two stages. There might be more iterations, or compiler might take more than one pass to compile a program, so it might have to read through it all to do one set of operations, read through again to do some other operations, but generally it's split out into these two key stages. The lexer, or lexical analyzer, reads the source code, takes any programming language keywords and replaces those with tokens, and it identifies any variables and data in the program, and it throws away the things like comments and spaces. This is passed as input to a parser, and the parser creates a syntax tree from the tokens, and this is where any things like syntax errors will be detected when the program checks to make sure that its program that you've written follows the rules of the programming language correctly. And this is then fed to a code generator stage which produces the machine code. And this can again be followed by an extra stage to make the machine code that's been generated more efficient or more optimal to ensure you get the best performance. So when we compile our files, we generally end up with some object files. These are shown here as OBJ, so object files here. What the linker does is it combines all of the object files created by our project, potentially with some pre-existing object files known as library files or lib files, and combines these together to produce the program output. The program output can be, well, on a Windows machine, for example, it could be one of three things. We could have a program that can run on its own right, an exe file, an executable. We could have a library file for use in other projects. So we've compiled our project, but instead of having a program to run, we've created a library file that we can then use in a different project. And the other output type is a dynamic link library. Dynamic link library is basically a library of executable code, again to be used by other programs. So a library file is used as input when we're compiling another program by the linker. DLLs usually go in Windows into the system folder, and they can be used by other running programs. So it's not used as input to compilation, but it's used as a library of code that can be used by other programs that are running. So the linker creates and uses lib files, which are libraries for using when compiling programs, and it can also create DLLs, which are libraries of code that can be used by running programs. And of course, to reiterate, the other possible output from the linker is an actual executable, a program that runs in its own right. During compilation, we take a program from a high-level portable form to a low-level form that's specific to a particular range of CPUs. And the same source code, one set of source code, can be compiled for a range of different machines, often requiring some changes. And some of these can be implemented in your program using things like preprocessor directives, those things like hash include, for example, so that depending on whether you're compiling it for a Mac or for a Windows PC, different libraries might be included, for example. Many applications do need the relative speed advantage of compilation while retaining a high degree of portability though. So sometimes we want another solution that has more or less the same speed advantage you get from compilation, but we might want a better degree of portability. We don't want to have to recompile the program for a different machine. And this is where we get the ideas of bytecode and virtual machines. So one solution is to do something called intermediate compilation. So instead of compiling to machine code for an Intel processor running on a Windows machine, for example, we might compile to some form of bytecode that's then executed by a virtual machine. A virtual machine is basically a kind of emulator. Instead of trying to emulate some other hardware, the virtual machine runs a particular set of instructions that should be able to be implemented efficiently on a range of different processors. So the virtual machine interprets code and translates bytecode to machine code. So the virtual machine itself is an interpreter. A very good example of a virtual machine in bytecode is with Java. So Java was developed and advanced and pushed by Sun as being a portable programming language. You could write in Java and have programs that would run on any computer as long as there was a virtual machine available. So although the virtual machine is doing interpretation, because the program has already been partially compiled to this bytecode, that interpretation should be more efficient than it would be if it was simply a basic program, for example. So for Java, now note, Java and JavaScript are not the same. JavaScript is a scripting language that can run on a web server or in a web browser. Java is a programming language that gets compiled to bytecode for running in a virtual machine. The bytecode is relatively low level and doesn't need to be human readable. And this means that the interpreter for the virtual machine is able to execute bytecode faster than traditional interpreted code. And virtual machines can be developed for different platforms. And this is, as I've said, so that one Java program can run on a Mac, on Windows, on Unix, and a range of different machines. They can also use something called just-in-time compilation to improve performance, which allows the processor to convert a particular command to machine code the first time it's interpreted, but remember that so that inside a loop we don't have to continually repeat the interpretation process. We do it once and we remember what the compiled version is. Another example of intermediate compilation is with the Common Intermediate Language, CIL, which is part of the Microsoft's .NET framework. It's CPU and platform independent, and there's a range of languages that can compile to CIL. The key example, or one of the best examples for CIL, is with C# and XNA. You can use XNA to develop a game that can run on Windows, and that runs on an Intel CPU. And you can also use the same code to run the same game on an Xbox, which uses a different processor architecture and has a different set of low-level commands that it understands. The bytecode from the intermediate language can be translated either to native code or run by a virtual machine. So you can actually do a second stage of compilation to create purely native code from the intermediate language. So there's a range of different options there for any program you're developing. Interpreted programming languages, compiled, and these intermediate ones, which are much more commonplace nowadays. As machines get more powerful, the overhead of using a virtual machine is not so bad, given you get this great advantage of having more portable code that's easier to get running on a wider range of different machines and hardware. Of course, If you can't find a programming language that you like or want, you could always create your own. This might sound a bit facetious, a bit silly, but developers actually are continuing to create new programming languages all the time and develop existing ones. There's a range of reasons why they might want to create their own programming languages, or you might want to. There might be some new hardware or computer science theories that you want to exploit to improve the software development efficiency. So some of the developments in programming languages are not so much to improve the performance of the program itself, but to make it easier to develop the programs, to improve on existing languages, to prove a theoretical point, or just for fun, for kicks. So let's look at a recently invented programming language, lolcode. So if you've ever seen the lolcats or ICANN has cheeseburger internet meme, which is pictures of cats with funny slogans, you might recognise this type of speech that's been converted into this programming language here. And here's a simple program written in lolcode. And here's what's going on as we go through this program. So, hi is the program start. Can has standard I/O. Use the I/O library. Visible, hi world. Print hello world message. Okay, thanks, bye. Program end. And a slightly longer example. Hi, can has standard I/O. I has a var. I'm in your loop. Up var 1. Visible var. Is var bigger than 10? Okay, thanks. I'm out of your loop. Okay, thanks, bye. And again, as we go through here, I has a is used to declare a variable. And the variable here has been called the var. That's the name of it. We can increment the variable, and is var bigger than 10 is a comparison to test if the variable is bigger than 10, and if it is, okay, thanks, it's going to end the loop. If you are going to write a compiler, well, luckily you don't have to use assembly to create a compiler. So the earliest compilers had to be written in assembly because there were no high-level languages to use. But you can use any high-level language to write a compiler, pretty much. And there's actually a wide range of tools that exist to make it easier to write compilers. Lex, which is a lexer, and Yak, a parser, which stands for Yet Another Compiler, have both been around for quite a large number of years now. And there's lots more up-to-date compiler tools available from sources like compilertools.net. Most programming languages, if you're going to create one, chances are it's going to fall into one of a small number of programming paradigms. Over the past 50 years or so, a number of different approaches to programming have emerged. Key forms or sorts of programming languages. And the increasing complexity and size of software systems has required changes to how people construct software over time. The two key forms of programming language are imperative and declarative. So an imperative program is a sequence of instructions where each instruction can change the program's state. And so a procedural or structured programming language like C or Pascal, and object-oriented programming languages like C++ or C# or Java are all examples of imperative programming. Declarative programming works quite differently in that code declares what the program should achieve, not so much how it should achieve it. And the key examples here fall under the functional and logical programming. So structured programming first. Program can contain blocks of code known as functions or procedures. Statements may call other functions or procedures. So when we have a function call, the program jumps to the procedure, and then after it's finished it returns to where it was called from. So for example, this is a C or C++ example. The main program runs until it reaches this point. So we start at main. We have a number of lines of code, and then we get to this one where we're calling the getMax function. So program executes this statement saying getMax input 1 and input 2. When it does that, the program execution jumps to the getMax function. And it will run through that function until it reaches a return statement or the end of the function, at which point it will return back to the main program or the calling section of program and continue from just after the statement where it was called. Actually the result of this getMax function will be stored in the variable num. So it actually returns to finish the line it was on in this case. Now, object-oriented programming appears to be probably the dominant programming paradigm that seems to be taught just now at universities. And there are a wide range of examples. C++, Java, C#, Delphi, Smalltalk, probably also the dominant programming paradigm in use in commerce and industry, game development and so on. Object-oriented programming groups data with related functions into what are called classes and objects. An idea here is that classes encapsulate some elements of design, and to use a class which contains data and contains functions all in one, then you don't need to know what's going on inside, you just need to know what data it has. Well, you don't need to know what data it has, you just need to know what functions it provides. And objects can communicate with other objects by passing messages to one another, and you can also create new classes, new types of objects from existing ones using something called inheritance. So a lot more to it than that, and many of you will be learning one of these programming languages as you go through your course. What you may not experience in your course, depending which course you're doing and which other modules are available, is something called functional programming. Programming languages like Lisp and Scheme, which have been around quite a long time, or Haskell, which is a little bit younger. These emphasize functions where the imperative programming languages emphasize the program state. So in a functional programming language, the result of a function depends only on the input parameters, not on any program state. May be less efficient in memory and CPU use, and relatively limited use outside of academia. So there are some universities that really do focus a lot on functional programming, where functional programming is very popular inside some areas of academia, but not so well used outside. There's also logical programming. A key example of this is Prolog, and it's based on propositional logic, which is a form of logic based on statements, and statements we can have rules and we can have facts, and then certain statements can be true or false, basically. So here's an example fact. Father, child, Mike, Tom. That means Mike is the father of Tom, who's the child. And here's another example rule. If parent-child XY, mother-child XY. This basically says if X is the mother and Y is a child, then X is a parent, Y is a child. It's obvious to us, but this is a simple rule that the Prolog program might work with. And here's a Prolog example. We have a range of facts at the top, saying that Trude is the mother of Sally, Tom is the father of Sally, Tom is the father of Erica, Mike is the father of Tom. And then we've got a few rules, so I'll do the rules from the bottom. So we've already seen the mother-child, parent-child rule. Above that, there's a very similar one. Father-child, parent-child. So basically saying if X is the father of Y, then that also means that X is also the parent of Y, which is obvious because parent is just a more general term for father or mother. And then the rule above says if Z is the parent of X and Z is the parent of Y, then X and Y must be siblings. So for any pair of children, X and Y, that have a parent, Z, the same, then X and Y must be siblings. They must be brother or sister to each other. Which allows us to enter a question to ask this program Are Sally and Erica siblings? And we can look through this, and it's easy for us to see, but the output of this would be from a Prolog program, simply the yes statement to say yes. We've checked these rules, and that's true. If we asked here sibling Sally Tom, the output would be very simply no. So note this program doesn't say how to perform this calculation, how to work this out. It's simply the collection of rules and facts, and then the Prolog program, when it's running, has its own set way of working through and working out the answer from this collection of facts and rules. There's a range of other ways in which we can distinguish or characterise programming languages, and generally these will fall under some of the other categories. So we could have event-based programming, and you can do that with C or C++. Parallel programming, so programming that allows multiple things to happen at the same time. Agent-oriented, and a whole range of other programming paradigms. And you can read much more about some of these online in your own time. As usual, further reading. If you are interested in this, there are a number of online courses available with video lectures on programming languages and compilers and developing programming languages and compilers. And there's just one example given there. And that's a complete course on the construction of programming languages, and it's quite advanced, but there's no harm in checking it out. Compilertools.net I mentioned, and as usual, there's lots and lots on Wikipedia to amuse and inform. And a few credits for the material this week. And that's all for now. Thank you.